Okay, this is our third video on hypervalency. We're going to do a little more practice on it and take a look at some cool stuff. I would like you to try to draw the SF6 molecule. So get out your paper, see if you can draw it. I'll pause the video. Okay, so I'm going to assume that you did that, and let's take a look. So all 6 valence electrons are used in bonding. So each pair of fluorines is going to break up a lone pair and result in 6, and it's going to take on this shape right here. Now, one cool thing is that sulfur hexafluoride is a cool substance. First of all, it's the densest known gas. It is so heavy, so if you have it, it'll sink below all the other gases. It's non-toxic and non-chemically reactive, and so it's used in electrical insulating systems. If you've got an electrical fire, you don't want to pour water on it because water conducts electricity and it can spread the fire. You can flood a room full of sulfur hexafluoride and kill the fire, kill the source of oxygen. Now, one of the drawbacks to sulfur hexafluoride, it is one of the most powerful greenhouse gases known. In fact, one molecule of it has the heat trapping capacity of 32,000 times that of carbon dioxide. And it is long lasting. It can last in our atmosphere for over 1,000 years. So definitely not something you want to release into the environment in any kind of large quantities. But watch this video.
Hi, I'm Rose. And I'm Anna. And we are going to be mad scientists. Everyone knows about helium. It's lighter than air, and if you put it in a balloon, it goes up. But some gases are heavier than air. Ta-da! Hi, I'm Rosie. And I'm Anna. And we have squeaky voices.
I'm Rosie. You're crazy, man. I like you, but you're crazy. I love you.
So I have another video I'd like you to watch. It posted on the Google Classroom about sulfur hexafluoride. Now, you notice on that last segment where the voices went deep when they breathed it in. That's because your pitch is based on the speed at which molecules leave your vocal cords. And so helium, being a super light gas, is going to come shooting out of your vocal cords at high velocity, and that is going to result in an increase in the pitch of your voice. So most people know about the squeaky voices you get from helium. Sulfur hexafluoride, on the other hand, being the heaviest gas, is going to sink deep into your lungs. It's going to take a lot of effort to push it out of your lungs against the force of gravity. So it's going to pass through your vocal cords at very slow speeds, and that's going to cause a deepening of your voice. Okay, so one thing to think about is how many bonds are these elements going to form? And is it going to be an even number or is it going to be an odd number? So here's a few rules of thumb that'll help you out with that. So any atom with an even number of valence electrons will form an even number of bonds. So let's look at an example of that. Sulfur has 6 valence electrons. That's an even number. So sulfur is able to form 2 bonds, 4 bonds, and 6 bonds. And the reason for that is, first of all, it has 2 unpaired electrons, so it'll start with 2 bonds. If something breaks up its lone pair, it'll form 2 more bonds, so that's 4. And if something breaks up its other lone pair, that becomes 6. The total number of bonds, though, cannot exceed the total number of valence electrons. That's the maximum number of bonds. So for sulfur, it is 6 is the maximum. You can't have 8 bonds. Okay, so let's look at another example. Any atom with an odd number of bonds, valence electrons, will always form an odd number of bonds. So for instance, phosphorus has 5 valence electrons. Phosphorus has 3 unpaired electrons and a lone pair. So it can form 3 bonds, but if its lone pair gets broken up, it becomes 5. Again, the total number of bonds, though, cannot exceed the number of valence electrons. Since phosphorus has 5 valence electrons, it can only make up to 5 bonds. It cannot make 7. All right, let's try another example. Please pause the video when you're going to try and draw the SF4O hypervalent molecule. Again, the number of bonds cannot exceed the number of valence electrons. And you need to determine, is it going to be an even number or an odd number? All right, so I'm assuming that you've drawn the molecule. Let's take a look. So this is what it's going to end up looking like. So the 4 fluorines are going to attach to the sulfur because the thing with the most electronegativity is going to attach to the thing with the least. So the fluorines will attach to the sulfur, not to the oxygen, because oxygen is higher than sulfur. So the 2 fluorines will come in and they'll attach to the unpaired electrons. 2 more fluorines come in and break up one of its lone pairs to form 2 more bonds. The oxygen then comes in and is able to break up the remaining lone pair to form a double bond so that oxygen can make the 2 bonds that it wants to make. Sulfur has 6 valence electrons and sulfur is making 6 total bonds. All right, let's try phosphorus pentafluoride. Penta means 5, like a pentagon. So this is PF5. All right, I'm assuming that you have completed that drawing. This is what it's going to look like. Phosphorus has 3 unpaired electrons. So the first 3 fluorines are going to attach to those 3. Then 2 additional fluorines will break up the lone pair to form 5 total bonds. All right, here's an interesting one. Xenon tetrafluoride. Now, normally we say that noble gases don't make bonds. Noble gases are exceptionally non-reactive. However, because xenon is a pretty large atom, things that are extremely electronegative like fluorine are able to, under certain circumstances, force those noble gases to become hypervalent. Doesn't happen very often. In fact, we don't see it in nature. We only see it in lab experiments. But let's see if you can draw xenon tetrafluoride. Tetra means 4. Okay, so let's see if we can figure it out. So xenon has 4 lone pairs, or 8 electrons around it. 2 of the fluorines are going to break up one of the lone pairs, and 2 of the fluorines are going to break up the other lone pairs, and we're going to form a structure like this, where 2 of the lone pairs are left untouched. All right, let's see if you can draw chlorine trifluoride. Again, pause the video, see if you can draw chlorine trifluoride. Okay, so chlorine has 7 valence electrons. There's 1 unpaired electron, so it can attach to one of the fluorines. 2 additional fluorines will come in and break up one of its lone pairs. So you're going to end up with something like this. 2 of the lone pairs remain intact. Okay, so let's try HClO. We're going to draw the 4 variations of the chlorate ions, HClO. So we're going to end up with something like this. Chlorine, again, wants to make 1 bond normally. Now it's going to make 3. And so the oxygen over here is going to break up one of its lone pairs, this oxygen here. There will still be 2 lone pairs remaining. All right, chlorine has 3 lone pairs, so let's see what happens. Now HClO3, so now we're going to add an additional oxygen to it. Where is that oxygen going to go? Well, as you're probably guessing, it's probably going to break up one of its lone pairs and form another double bond. So now you see that it looks like this. Now we have one lone pair remaining. We've got these two oxygens. The OH remains off on the end. All right, what about HClO4? I think you're probably seeing the pattern by now. A fourth oxygen is going to come in. It's going to break up the last lone pair, and we're going to get something like this. Now, notice how many bonds are around that oxygen. That chlorine. There are 7 bonds. We've got 2, 4, 6, 7. Well, chlorine has 7 valence electrons, so it's allowed to make up to 7 bonds. So, chlorine can make 1 bond when it's just making a normal bond with its unpaired electron. It can make 3 bonds when it breaks up its lone pair. It can make 5 bonds when it breaks up 2 of its lone pairs, and it can make 7 bonds when it breaks up all of its lone pairs. So again, it's always going to be an odd number of bonds for an element with an odd number of valence electrons. All right, we have one more to draw here. Iodine heptafluoride. Hepta means 7. Pause the video, see if you can do it. Iodine has 7 valence electrons, but the fluorines only make 1 bond. So we're going to have something that looks like this, where there are 7 fluorines attached to each of its unpaired electrons. All right, so that is hypervalency. See you next time.